Um, yeah, Jeff. I don't think you know what that word means. 6-3, for example, at the very least, it's got Frobenius in it. I mean, come on. Frobenius. Have you ever heard of Infocom? Zork? Have you ever heard of Zork? No? Okay, that's a while back. That's back when we had games for a computer that had no pictures. They were just all words, and little geeky Jeff loved the shit out of that. But it just sounds like it belongs in this game, Frobenius. Anyway, he had a method. Section 6.3 is not that different from 6.2. There are some intricate stuff into why the certain relationship for what they use R for exists, but they just kind of give it to us. So it's just that R equation is related heavily to the M equation, what do we call it? The auxiliary equation, right? It comes from the same sort of place. Anyway, so 6.3 is completely doable if you wanted to do that extra credit. There's just a lot of explanation about why things kind of work the way they do. And I thought Laplace was just more important to get into than to get lost in the weeds of why things work the way they do in 6.3. So we got really small steps into Laplace last time. We just defined what it was and then tried to remember how to do, by parts, making sure that we all remembered by part stuff. So the Laplace of some function is that thing. Now, there is a history to this. It's related to probability theory. It's related to the Fourier series. It's related to a lot of different things. Laplace got his name stuck on it because he's the one that kind of organized it and used it in more specific ways, but trust me, it was around before Laplace. He just happened to really use it the way we use it today. So we said, let's name it after this guy. I'm not going to give you the whole history lesson. Let's just remember how this works. How would you do Laplace of, last time we did T. I don't want to tune it. I wonder if you guys remember, do you remember how this works if you do Laplace of cosine? Do you remember how that works with this? Let's see how far you can get with that. Try to do the Laplace of cosine. And then I'll stop torturing you and give you the table that translates all this for us. Any of you guys remember ahead of time what's going to happen here? This one's a funky ass one that if you know sort of ahead of time what to do, you can just keep doing it forever. You know what I'm saying? You should only have to do 2 iterations. Because after 2 iterations, this will become cosine again, right? So there's that little trick about, you'll have on one side, you'll have the same expression, so you can just treat it like x, add it to the other side, or whatever, just try whatever it is. So here, what are you letting u be? Cosine, okay. So if you let u be cosine, what's du? Negative sine. And dv then has to be e to the negative st dt, which means v is over s. I like it. From a t. Okay. Now, if you would have chosen, it doesn't really matter. It'll work either way. You could have chosen the other way, it doesn't matter. So, here we go. So then UV, so you get negative e to the negative st cosine t over s uv minus the integral of v du. V is negative, so it'll be plus 1 over s integral. Oh, is this negative also? Yeah, Jeff, you can do it. V du, bam. 1 over s e to the negative st sine t dt. Now this is from 0, and we'll adopt the book's convention, which is fine with me actually. I'll just do it because the book does it. No, I have to put the low limit because you can't throw infinity into something. I always, please dear God, never do this unless it's showing me a form of something, right? You can't. In fact, at one point I had a class where they just wanted, I said, no, just put BFN for big freaking number, right? Don't put an infinity in there. It's impossible. If you can't pick infinity up, you can't put it somewhere. Oh. And if you can pick infinity up, see me. I want to see that shit. So when I plug infinity in here, of course, we're assuming s is greater than 0 like before. When I plug infinity in here, this goes to 0. When I plug a 0 in, what do you get? 1 over s. And then that's minus this, right? So infinity would be this, and then minus, so it becomes 1 over s, minus, and now I've got to do what to this? By parts again. So if you, now you get, the trick to this is if you did u equals cosine, you should probably do u equals sine. To be honest, it works the other way too, but oh. Du would be cosine, dv then is e to the negative t, v would be e to the negative t over s, just like before. So then you get 1 over s times uv, that's negative, you can see. Negative e, negative st sine t over s, turns to infinity, coming to infinity, thank you. Minus the integral of v du, and that'll be, so this time it'll be plus integral, I can put 1 over s, integral of e to the st cosine, it's negative there, Jeff, there you go, buddy. Cosine t, bam. So I get 1 over s. When I plug infinity, it goes to 0. When I plug a 0, it goes to 0. So then I get minus 1 over s squared. And what's this? This is the original problem, right? So this is actually Laplace, yeah, cosine t. That right there, right? Cool. And back in 180, you would call it I. I don't know if you guys remember that. That's the integral, we'll call it I. Yeah, so then you can add it over this side. So if you wanted to, you could say, so I got Laplace cosine t equals this. I could, there's a few different ways you could do this. You could multiply everything by s squared. Add this over, so you get s squared plus 1. Oh, Jeff, you can do it, buddy. There you go. Laplace equals s. So you get Laplace equals s over s squared plus 1. Freaky. I think I did that right. Let's see. I don't know. Yeah, let's see. Yeah, cool. I like it. So the Laplace of cosine is just s over s squared plus 1. We didn't do the Laplace of sine, did we? But that's all right. Let me go ahead and give you this. I mean, you could go a little insane, and you could do, is everybody semi-decent with what happened up here? Are you guys cool with what I just multiplied everything by s squared just so I can get rid of all the fractions? Call this L just so it's a single thing. Added this over, so I got S squared L plus 1L. And divided by the shit I don't want. So then the Laplacian of cosine is this. I like it. Yes, sir?
What's this?
S is the variable that is used once you transform a function. So Laplace of a function of t becomes a function of s. You guys see it? The dummy variable here is t. The actual variable is s, which is really, really, really nifty. And this happens a lot. It's not always s greater than 0, but it is mostly that. Sometimes you want to make it something different. Let me give you this. This should feel familiar to when you first learned intervals, and then you learned there were tables that had all the answers there waiting for you. This is nowhere near a complete table. If you just do a Google search of Laplace transform table, you'll get way more than you know exists. So the true power of this transform, bless you, it's not something that they overnight realized what they could use it for. So as a student, you don't see that. It was used for a lot of different reasons. It kind of existed. People were playing around with it. Laplace was the first one to really realize what it could be used for. Notice how there's Laplace transforms, and then there's inverse Laplace. That's what we're talking about. If I can transform something using Laplace transform, work with it in a simpler way, and then transform it back. That's where the true power of it lies, right? So before we start actually using Laplace on DEs, there's a few things we have to be aware of and able to do. You're not always going to have cosine KT. You're not always going to have something nice like 1 over s minus a that you have to transform back. You're going to have little tweaks that you have to make. And that should be familiar too. So when you first learned about interval tables, some of you guys might have been excited or you already knew about it. But then what sucks is the interval table gives you the general form. You have to match your problem up with it and say, what do I, oh, that's a. So a is 3 over 7 actually. Oh shit, you have to match with what you got, with what the form is. That same kind of thing is going to happen here. So just to make sure everybody can read that sucker correctly and can read all the way to the bottom, what would the Laplace of 3t to the 4th be? Yeah, the nice thing is that 3 is based on integration. And the inverse is based on differentiation then, so it should be, the constants should just come out all the time. And you can put a constant in, you can put like a 1 over 7 if you need a 7 inside, just like any interval. So that 3 can come out. Good. Now you can identify n as 4. Yes, n plus 1? Right.
Yeah.
Yeah. 4 factorial is 24 times 3. Cool. I like it. So what about, let's see. What about the Laplacian of square root of pi sine of 11.2 t? That's right, pi.
Is that 11.2?
The square root of pi is just a constant multiplier. Get out of there. Sine goes to So what's k in this case? 11.2. So it'll be 11.2 over s squared plus 11.2 squared. Careful, it's not sinh. Yeah.
Is it minus?
It's not sinh.
Oh.
Yeah.
Okay.
I won't use sinh and cosh too much, although they do show up a decent amount in engineering and electrical stuff and all that stuff. All right, not too bad. All right. Where it gets a little more interesting than this, because this is pretty straightforward, is the reverse. And oh, you're going to be very happy to find out. Notice how the inverse Laplace of 1 over s minus a is e to the at, right? Somewhere in the back of your brain realizes that means that there's probably going to be some partial fraction decomposition in our future, right? So it's kind of related to integrating some ugly-ass big partial. The fraction thing that I got to break into its parts so I can see the logs and whatever else happens. It's related to that. So, for example, if I had the Laplacian of 4 over, the inverse Laplace, let's say, of 4 over s squared minus 9, which should be 2 equal. That's up to you. You can either do like the, what am I trying to say, the partial fraction stuff with the 4 in there or not, because it's just a constant, it can come out. It doesn't really matter. So hopefully you guys realize, real quick, a little side note. Laplacian and inverse Laplacian are linear operators, just like integration and differentiation are linear. What the hell does that mean? What's the inverse Laplacian of 1 over s minus 2 plus 1 over s? So that is the inverse Laplacian of, you can make an algebra, can you? There you go. 1 over s plus 2, minus 2, sorry. Plus the inverse Laplacian of 1 over s. That would be e to the 2t plus 1. Is that cool? So then that guy makes total sense. If you break that sucker apart, you end up with something vaguely like that. You can attack it piece by piece.
Why isn't that one just like sine h or a over s squared minus k squared?
Well, I mean, so you can attack this in two different ways, to be honest. The way I immediately thought about it was as a partial fraction decomposition. But you can also, what's kind of wrong though, that's kind of easy to take care of. Yeah, these don't really match up the way they're supposed to. Now the difference between sinh and cosh, there's a huge difference, right? Sinh, cosh is the one that requires the top be dependent on s. Sinh is the one that says the top can be any constant it wants to be. So this has got to be, like you said, related to sinh because there is no s on the top. I can't make an s show up. It is constant. I can take a constant in and out. So what should be on the top if I want to make it match up with that? 3. So all I got to do is take the 4 out. And how to make a 3 show up in there, of course? Sort of gave it away there. Yeah. So this will be the invert. Oh, sorry. This will be sinh or what? I like it. No, but now I'm curious. What would this look like if we did it? This is kind of nifty. If we did it the other way, what would happen? And I know you guys are just trying to avoid the partial, but you can't always. I just gave you one that you could. Too bad. Not always. To be honest, there actually is a way you can kind of avoid it. Once we get through the next section, I'll let you guys figure it out if you can. But if I attack this with partial fractions, what would it look like?
S minus 3s plus 3.
Yeah.
Thought, A.
So it'll be A over S minus 3, B over S plus 3. So 4 equals A, S plus 3, plus B, got it. S minus 3. Since it's just a 4, it's kind of easier just to go. But A plus B has to be what?
4 over 3.
Is there an S term over here? So what's A plus B got to be? AS plus BS is 0. Yeah, A plus B got to be 0. And what's 3A minus 3B? That's got to be 4. So A is negative B, which means that this is actually 3A plus 3A. 6A equals 4. A is 2/3. I guess, well, I mean, it's just substitution. If A is 2/3, B is, that's crazy. Right? So let's see what we got. Let me take this away. Go in. A little side note. So then we got the Laplace of this is the inverse Laplace of, where'd it go? Let me put 2/3, that's the A one, minus 2/3, 1 over S plus 3. So what would this be? This is 2/3.
Either
Either 3t, 1 over S minus A. You with me? And remember, what's sinh and cosh based on? Do you remember? They're based on exponentials, right? Go back to the, so of course that relates to the two different ways to do this problem, right? Because one way is going to have exponentials in it, and the other way's got sinh and cosh. I mean, they match up. Minus 2/3 e to the negative 3t. If you play around with this in the definition of cosh and sinh, you actually get the same thing. Believe it or not. It's probably a little easier to throw the definition in here and show that it's this. Yeah.
What is the S again?
So again?
What's the S?
That's just, so you start with a function of, so you start with a function of t, and after the Laplace transform it becomes a function of s. I like it. That's it, to be honest. I like it. It's just a dummy variable, because s can't be the same as t necessarily, but they are kind of related for a minute. All right.
We able to get that answer instead of the 4/3?
If I gave you this problem and just said do it, I would accept either way. Because there are multiple ways to do it. Now, I started with a nice one just because, but I mean, obviously, if the bottom is, this is where you guys might be able to figure it out, how to do it either way. I mean, if the bottom, if I would have done this instead, you can do it, Jeff, it doesn't matter. There you go, buddy. Now, can you relate that to sinh? Yes, if you can. If we get through the next section it deals with translations. So you can imagine, can't you, what should be here if I want this to be a perfect square? You can complete the square, do that kind of thing. So there is a way around it, but it's up to you which way you want to do it. If you hate partial fraction decomposition with a passion, then you can find a way around it. But at the same time, you should really know freaking partial fractions. You just should. All right. You've seen this kind of thing before where you throw this off to the side for a second, you put plus 16 here, are you with me? Minus 16, so that'll be the minus 36. This will be a nice shift. It'll just be a shift on the s-axis, and that's what the next section talks about. How do you translate on the s-axis? And what's that mean? I like it. Coolness, coolness. All right, so let me do this. I gave you the Laplace transform thing, right? I want you to try to do these. Don't worry about the back yet. Put the back there just so I didn't have to just so you have it for later. We're gonna do that, hopefully before we leave. Maybe not. Sure. Probably not. You guys know when the next test is?
No.
Yeah, dude. That Monday after Thanksgiving, because I'm evil.
Do we have that Wednesday off or?
Yeah, I give you guys that Wednesday off, so I don't want to hear any crap. You could have the test on Wednesday instead, right before Thanksgiving. So, you're welcome.
Will this final review after that?
What's up?
Really? That's good.
Yeah, Thanksgiving is next Thursday. if I remember correctly.
Is it just gonna be like final review after that?
Yeah.
So like 3 days and
Pretty much. Can't remember now. It's all on that sheet. I made it up a long time ago. So I want you guys to do this side. Don't worry about this side. You can look at it. The side with derivatives, which is going to relate to how it handles DEs. All right, so everybody's curious about that now. But do this side, the one with all of problems on it. Try those. They're just like the ones we did up here. And by the way, I will give you these. I'm finally, for everybody who's so angry at me for not giving you anything, making you remember everything, because I'm just that kind of person. I will actually give you this to use. All right. Especially because it's right at the end. You don't have a lot of time to play with it, so I'm not going to expect it to stick in your head too easy.